Hello everyone, good day. Today we are at our last lecture of this field course, and this is lecture number 17. In the last 4 weeks, we learned significant topics and we gathered significant information from the region Ghatshila, particularly focusing on several aspects of field structural geology. In this lecture, the aim is to review all these documents. So, what we are going to learn in this lecture is outlined here. As you can see, we will first give you kind of week-wise summary, then we will talk about the primary and secondary structures that we have learned. After that, we will very quickly review the overprinting relationships, and together with that we finally come to interpret the structural setting of the Ghatshila region. So, what we are going to do in this lecture, actually I will show you a number of images at the very beginning. These images are field photographs, and some of them you have seen during the movement, or some of them you did not see. So, it is a combination of things that we have seen and things that you did not see. And the challenge here is I will show you something and then you have also to interpret them by yourself, or at least you try to, that is my request. More than that, in this entire field course, we tried to give you in a very simplistic form the explanations of the structures that we have seen. Now, as I said at the very beginning of this course, that for a single feature there could be multiple explanations and interpretations. What I have given is the simplest form or a particular school of thought, but there might be some other explanations and interpretations which I did not provide, but there might be some other interpretations. So, in general you do not have to believe what I said in terms of interpretations. You may come up with your own interpretations, or you may read literature and figure out some other interpretations as well, and these are all fine to understand the subject. In the first week, we mostly introduced the course, then we talked about different aspects of field geology, particularly we covered tools and other things that one has to carry to the field. Then we talked about field locations, where we have done the field work, we gave a very brief overview of this region, that is Ghatshila, and then we also learned a little bit of theory on measuring and plotting the data. On week 2, we talked about mostly primary and secondary structures, and at the end we showed you how to do lithostructural mapping, and we also plotted the data in the map. In week 3, we focused on ductile deformation, but again in the entire range of ductile deformation we did not cover. We mostly restricted ourselves in studying fold and different morphology of folds. We of course talked about superposed and overprinting relationships in polyphase folding. In the last week, that is this week, at the very first 2 lectures, we talked about brittle deformation and some direct strain analysis from field structures, and this is the last lecture, which is the review 1. So, at the very first, it is important that we review what we actually learned, that how to study rocks in the field. And here in this slide, I have given a number of points that actually are useful before you go to the field. The first and foremost thing before you go to the field is gather information of the region you are going. There is hardly any region that geologists did not work on. So, there must be some literature, some texts. It is important that you gather these information, read them and prepare yourselves to figure out where to go and how to go. And try to see the rocks in the field as much as you can. Of course, these has to be in situ, not drifted or tilted and so on. So, that is important. You examine and identify the rocks, and while doing this you ask several questions. Is the rock isotropic or anisotropic? Is the rock homogeneous or heterogeneous? If the rock is deformed and metamorphosed, then try to understand what is the grade of metamorphism or metamorphic phases, and this you get from mineral assemblages. And of course, you need to ask the question whether the rock is deformed or not. So, once you are convinced that these rocks are deformed, then you look for different planar and linear elements of these rocks. So, you look for what are the primary features, what are the secondary features of these rocks, and of course, once you are looking at, you also ask this question that if I am looking at which section. So, as we have understood that different sections may expose the rocks or structures differently. So, it is important that you try to visualize that which section we are looking at with respect to the structure we are trying to interpret. And of course, you need to do measurements of these linear and structural elements, take notes of them, and finally plot the data before you interpret them. Now, we will talk about primary structures, and we have understood from the field that if the primary structures are preserved, that means the rocks are of low metamorphic phases, then they provide you the some of the initial things of these rocks. So, they provide depositional information, they most of the time do act as excellent markers to understand the regional deformation, and some of them are suitable for strain analysis. We have learnt it using conglomerates, we have learnt it using deformed convolutes and so many other features, and of course, they reveal the deformation by their distortion of shapes. And continuing to this topic, the first and foremost thing, if we see primary structures, it is important that we first try to identify and understand what is the bedding plane. That is, we have defined in our course that this is always S0. This is how we have defined, and people generally define it this way. So, here are some points to understand the bedding planes in the field, or to recognize the bedding planes in the field. So, presence of sedimentary structures along strike, if you see them, yes, you are looking at the bedding planes or traces of the bedding planes. Then you may also look for compositional or color variation across strike, thickness variation across strike, grain size variation across strike, and of course, inconsistent layers. We will examine all of them in the following slides using some photographs. So, what we see here to identify bedding planes, as you can see that this is an exposure where we see some traces of planes. So, for example, this one, then this one, this one, this one, this one, and so on. We also see some features here, and we know from our lectures that these are cross beddings. So, once we see this kind of structure, so these are traces of the bedding planes, and we identify them using the cross beddings. In a similar way, here in this image we see that this we did not see in the field course, but these are all from Ghatshila. You see these black things which are kind of sagged down, and I tell you these are load balls, okay? And you can see some of these black things are also concentrated around this. So, this is your bedding plane, this is how you identify that, and it also tells you that this is the Younging direction. Then we also see some black features here. These are again kind of load balls, and they are developed just below this horizon. So, this tells you that this is the trace of the bedding plane on this quartzite rock. In addition to this, you can also see some traces of cross beddings on this plane. So, that both features, this one and the cross beddings, they clearly demonstrate you that these are essentially bedding planes. Here the next image is little interesting. We actually see traces of two planes. One moves like east west or horizontal with respect to the image, and another you see kind of some mechanical layers going like that. Now, again using what we have just learned, that using sedimentary structures along the strike can help you to identify bedding planes. We can see here that we have some traces of sedimentary structures, and again these are cross beddings. So, that clearly tells you that these are the traces of bedding planes on the surface. Now, again some sedimentary structures that we can see here. These are ripple migrations that we have learnt from our primary sedimentary structures, and we can clearly identify that these are the traces of bedding planes on this exposed surface. Now, in the second image, what we see here, that we see the color variation or thickness variation. We can clearly identify this alternate dark and white layers. We have seen this place, and again we can very confidently mark these layers as the traces of the bedding planes on this surface. Okay. You can see their thickness is varying. This is pretty thick, and then here you have numerous laminations of alternate dark and light colors. Okay. Now, you can also identify bedding planes, as I said, by alternating color bands, and here we have a large exposure. This is a drone view. These people here, you can use them as a scale, and you actually can see that you have some color variation, goes like that. This is a white layer, then you have some here alternate dark and white bands, and they clearly indicate that we are looking at the traces of the bedding planes on this exposed surface. Here we see also the thickness variation, but the composition mostly remains same in the first image. As you can see here, they are all quartzite, but their thickness did vary. And little further, if you look here, you also see the traces of cross beddings here and there, and that also confirms that you are looking at the traces of bedding planes here. We sometimes see the traces of bedding planes as striping lineations that we have learnt in the field, and you can see that it is present here. And you also can see that this part and this part, they are compositionally different. Then we saw some syn sedimentary structures in the field, and we saw them in various forms. We actually demonstrated some of the very simple sedimentary syn sedimentary structures that we have seen in the field. But in the field there are some very complex syn sedimentary structures, and here I am trying to give you some of these as an example, and if you ever go to Ghatshila, you may try to interpret them. However, you can see here that these are, as we have understood, the traces of the bedding planes. You can see that in this little area you have alternate color variations, and then you see the traces of ripple migrations here, here and so other many places. And here these are, as we may see, that probably these are buccal folds, but they are not. They all have developed either due to ripple migration or some syn sedimentary deformation. In the field we have seen convolute laminations. I tried to give you the idea of convolute laminations by making some sketches and so on. one of the TAs, Rajiv, he also tried to give you some ideas of convolutes and related features from Dhalbhumgarh airstrip, but here in this slide you see two photographs and they are extremely complex. So, these are essentially convolutes, but multiple sets of sedimentary deformation together with their rotation and other things happened here, and therefore, you generate this kind of very complex sedimentary deformation. Now, once we more or less got convinced with how to identify the bedding planes and related sedimentary and sedimentary structures, then the next task for us was how to identify the secondary planes. And in secondary planes, we mostly identified S1, S2 and S3 in the field. To identify secondary planes, we have some points here. So, you do not expect sedimentary structures along the strike unless S1 and S0 are parallel to each other, but that you can examine. Then compositional variation across the strike, you generally do not expect in low grade metamorphic rocks when you are talking about or when you are trying to find the secondary planes. However, in high grade metamorphic rocks, this information is not valid. There actually you see compositional banding and they define the cystosity. You hardly see thickness variation across the strike if the rock has a homogeneous composition. However, if the rock has heterogeneous composition or the rock is anisotropic, that means you have alternate variations of composition and therefore alternate variations of strength, then you might have developed in some places very strong foliation, in some other places you may not develop strong foliation. And this we have seen in the field. We have seen in quartz rich layers we hardly found foliations, but the moment we moved to mica rich layers, we found that dramatically changed and the place is characterized by significant number of foliations. Secondary planes are generally consistent layers and they appear in mechanical form like we have seen and we will see some. And what is most important, they can be of different generations and they are marked by secondary structures. We will see this, we have seen this in the field and we will see this more in some of the following images. So, what we see here in this image, this is from Ferrighat, we see that these layers, the traces of the layers here and there, these are actually S1, okay? And we have learned that S1 should be always continuous, okay? So, in this field scale here we see these are continuous foliation or S1, these are, and these planes are exposed as you can see here or here, these are the planes of foliation and here you can actually come and measure the orientation of the S1 plane. However, if this foliation plane is further deformed, then it develops secondary foliations. So, what we see here in this image, this are the traces of S1 which is continuous foliation, and then this foliation most likely got compressed and therefore, you can see crenulation. So, these foliation planes, this continuous cystosity got crenulated and because of this crenulation you can see throughout this exposure you see a linear feature like that. We learned that these are crenulation lineation, we will talk about it later soon. But what is important that because of the deformation of S1 here and what we learned that because of the deformation of S1 here, we developed this granulation lineation, and of course, these are penetrative structures. So, in 3 dimension you develop a set of foliations, and these are spaced foliations. So, in other words, if I try to make a cartoon diagram here, at least with respect to this image, we can say that okay, the foliations or S1 are like this. So, these are the traces of S1, and then if you compress it this way, then here the S1s are crenulated. These probably will remain straight, and here you see the traces of the crenulation axis, and therefore, you also develop one side. So, here this plane, as we can mark here, is S1, and which is continuous, and due to deformation this way it develops another set of plane here. These are S2 and these are spaced foliation. And in the field we learnt how to identify them, and of course, we also talked about their overprinting relationships. In places we have seen the axial planar cleavages directly. We will demonstrate later that the foliation we have seen in the field, measured and encountered, they are all axial planar foliations. And here is an example. We have almost a profile section of a fold, very open gentle fold, and now I am sure you would not have any problem in identifying that these are the traces of S0 or the bedding plane. And you can see if this is the hinge region, we have developed axial planar foliation. And the way we are saying, you see this layer, this packet, for example, if I consider this is mica rich layer. So, you see numerous foliations have developed here, and this layer in particular is quartz rich layer, and we hardly developed any foliation here, or at least we do not see them visually here. Okay. So, different types of planar features we have seen S0, we have seen S1, S2 and S3. S0 is primary, S1, S2 and S3 are secondary axial planar cleavages of different generations of folding. We have seen different type of lineations in the field. As you can see in this image, we talked about this. So, we see that this form surface is S1, and then this S1 got deformed in this direction if we consider this image in particular, and we see this beautiful small fold like features. Okay. So, this is mica rich layer, and therefore, it readily formed the crenulations, and these axes provide the crenulation lineation. We can see them in a different scale, and here actually we have seen this exposure. There are 2 different kinds of lineations. One, as you can clearly understand, is defined this way. These are crenulation lineation. Apology for my not so direct drawing. Okay. And then we see here another set of lineation. This is a beautiful exposure we have seen in this field, and we learned that if we zoom this, we know that here we have a garnet grain, and along this we have pressure shadow, and they gave rise this beautiful pressure shadow lineation. Okay, let me put this arrow. Okay. We have seen mineral lineations at many different places, and mineral delineations are defined by minerals in one place that we have seen. Again this surface is S1 and we have seen this, I tell you these are biotite grains. So, overall orientation of these grains are like this and these are mineral lineation. Okay. When we looked at this contact between the dolerite dike and the host rock mica schist in Ferrighat at this baked zone, which we defined as the contact zone of this hot dike and relatively colder host rock, we have seen minerals have developed along this baked zone and they also defined a lineation. These minerals are amphibole and therefore, these are also a type of mineral lineations which are aligned in a particular direction. All these lineation that we talked about right now, these are all penetrative lineation. We have seen non-penetrative lineation as well and these are slickened lines. So, this exposure we have seen and we have understood that these are slickened lines. There was another exposure where we saw the conjugate joints. We did not show you this exposure, but you can now clearly understand comparing what we have seen that this is a slickened side or slickened surface and these are the lineation and these are the steps that we have demonstrated here, the steps like this here. Okay. So, the idea is that we have shown you a very particular exposure, but not necessarily everywhere in the world you will see them in a similar form. So, seeing rocks is very, very important. So, let us talk about the brittle structures that we have seen, and if I ask you that what is the most significant brittle structure that we have seen in the field, just think a little bit. You probably will talk about the conjugate sets and other things, but I tell you the significant one is the dolerite dike that we have seen in Ferrighat. So, here is an image, the drone image, you can see this is the dolerite dike. So, the host rock got fractured and then this dike intruded. In this dolerite dike we have demonstrated a lot of things for brittle deformation. For example, we talked about the conjugate sets of shear fractures. In this dolerite dike we also talked about the anechelon or tensile gushes. We have also seen a number of veins, quartz veins other than these tensile gases. They have intruded in different times, in different generations, and within these quartz veins we have noticed some particular structures that we did not show you. Again, as I told that we are not going to show you everything in the field, but in this review lecture we will show you some other features so that you can figure these things out. So, what we see here in these two images, these are known as wing fractures. Okay. How to interpret them? You can see if I try to draw here, we have two tiny fractures here and then you have a major fracture. We also see here in the other image you have a single fracture going like that and we have two fractures going like that. What happens, because we know that this is in the vicinity of shear zone and the dike has underwent shear deformation from this tensile gases, sometimes these fractures cannot propagate in this side. Okay. So, therefore, you can understand the fact that here in this case, if the shear sense is like this, that is sinistral, which is in most of the cases we have seen. So, because it cannot propagate here, but this is already pushing and this is blocked. So, basically you are generating a tensile stress in this at the tip of this fracture, and as a result these fractures do form almost at right angle to the fracture wall, and then they vanish after a while, because this tensile stress is not present when you go away from the main fracture. And a similar way it happens, you see it almost formed at a right angle to this main shear fracture. So, again here this is happening. Now, you can ask me the question that this is not the fracture tip. Yes, your observation is right, and thanks that you asked. Here what could happen, again this is one of the interpretations, that the friction in this area probably went very high, and therefore, it could not propagate at that time. So, it formed this fracture this way to release the stress accommodation. As I was talking about a while ago, that the quartz veins, they also contain number of different structures, and you can see here in the first image, this is the quartz vein, and you can also probably identify that the host rock, this mafic dike, they also define a fabric. Let us not go into that right now, but this quartz vein you can see some consistent fractures inside. Okay. One set is of this orientation, another set is of this orientation. From theory lectures you probably know what these are. So, these are low angle Riddle shear fractures and high angle Riddle shear fractures, and from this you can actually demonstrate the sense of shear. The next one, very interestingly, you can, if you compare with this, here we see the fracture planes are very distinct, but here we see some probably fracture planes, but this particular quartz vein is actually defined by a fabric. Okay. And this fabric is very closely resembles what we learned in ductile shear zones, that these are very much similar to S fabric. So, you see that how complex it could be. A dolerite dike intruded, that was a brittle deformation. Then we see some fabrics inside the dolerite dike, and then we have seen quartz veins intruded. They again define a brittle deformation, and then within the quartz vein we see two different kinds of deformation. One that defines very brittle here, and then another is defining a ductile deformation. So, eventually a little observation can tell you a lot of things in the field, and it is important that you document each and everything. Now, we will try to interpret the overall deformation of Ghatshila region, and we will mostly take the help of the data that we have measured. At the same time, we will see the disposition of the structures that we have seen in Ferighat and in Harindungri village. We particularly will take the help of these 3 quartzite bands that we have seen, their deformation and the data measured from there. We also will take the help from the different mica schist outcrops that were exposed in and around the Harindungri region, and all these are shown in week 2 and week 3. Let us start from the Ferighat. In Ferighat, the data we measured, the general trend that we have seen, though there are some variations, but bedding planes S0 is in general strikes towards 150 degrees and it dips 70 degrees. The foliation S1 plane, the primary foliation that we have observed, that is 290 degrees and 30 degrees, that is the attitude, and the mineral lineation we have seen is 15 degrees towards 060 degrees. Now, I did not put the other lineations here, and I will explain you just in a while. So, if we try to work with this data, let me first draw kind of a rough stereo net. Okay. So, this is the primitive circle, and let us consider this is north, this is east, this is south, and this is west. So, bedding plane that strikes 150 degrees. So, it approximately I just draw it like that, and 70 degrees. So, it should be I think it would be more towards this 70 degrees. So, it is steeply dipping, something like that. So, let us consider that this is the bedding plane. The foliation plane 290 degrees, 30 degrees. So, gently dipping foliation plane. So, I can consider it something like that. I am doing it very approximately. So, this is 70 degrees, and let us consider this is 30 degrees. Okay. So, clearly bedding foliation intersection gives you the fold axis, and this is the F1 fold axis, and we know that from our data that the fold axis is very low, plunging here, that we have measured from the striping lineation exposed on the foliation surface. And the data that we more or less the fold axis was plunging around 15 to 20 degrees, and it was plunging towards 320 degrees. Okay. So, that is the fold axis. Now, if I plot the mineral lineation that was also we have seen on this foliation surface, they were somewhere like this. Okay. If I try to plot here, this is how they concentrated. Okay. And if we try to measure the angle between the first fold axis and the mineral lineations that we have observed, this is almost 90 degrees. Now, what do you interpret from this? I let you do that, I am not going to explain it to you. I am sorry for that, something you need to do and figure it out by yourself. But the information we are taking from the Feringhart further to this is that the bedding plane S0 and F1 and sorry. So, the interpretation, some further information that we can take from Feringhart is that the relationship between bedding plane, that is S0, and the first foliation, that is S1. From the data we see that they are more or less orthogonal to each other, and that clearly tells us at Feringhart we are at hinge zone. Okay. And another information is the fold axis. So, fold in Feringhart, though we did not see in particular an outcrop scale fold or even a small scale fold, but at the hinge zone we have measured the fold axis F1, which is very low angle plunge, okay, 15 to 20 degrees. So, we can say that fold here is a plunging fold. Okay. Let us take these two information to the overall deformation of Ghatshila region. And this is the map that we have prepared in this field course, and in these 3 sets of stereo net, this is the first set, second set and third set, these are the data of the 3 quartzite bands. And we more or less are convinced from this data that these 3 bands were deformed synthetically. What is the difference between Feringhart and this Harindungri region? By the way, Feringhart is somewhere here. The most important information that we get here, that we discussed in the field as well, is this fold axis. It is much steeper. And if we remember in the third quartzite band where we have seen an exposed fold, that was almost reclined fold. So, the plunge of the fold axis was almost 82 degrees. So, from Feringhart where fold axis, the F1 was around, the plunge was 15 to 20 degrees, just a few kilometers we see the fold axis changed significantly. We have seen here the bedding cleavage relationship is orthogonal to each other. So, this is also a hinge zone, and when we are working near band 2, somewhere here where we have seen all these thin sedimentary structures, the hook shaped fold and so on, there the bedding and F1 relationship was almost parallel to each other. So, that must be a limb zone. From our stereo net, we also identify that this particular 3 quartz bands are folded, of course, but from here if we try to go to a little larger regional map, particularly if we go back to our old map that is prepared by Professor Khitin Naha, we actually mapped this particular area. Okay. The Subarnarekha is flowing like that. But we can see that it is going towards this side, and after crossing the Subarnarekha it is going like that. So, if we try to extend this one here, probably all these 3 quartz bands are moving in this way, and here they are probably moving in this way. We did not map that in this field course, but people have mapped it. We have seen a little Nala, Lokchoriya Nala or Lokchoriya river has we have seen this river is going like this, and it has some branches and so on. We have also seen the Ghatshila main road going like this way, and at the hinge zone we have encountered number of faults or slips. And we see the entire drainage pattern including the Ghatshila main road are actually following the faults, and you can see them in more detail if you look at in Google Map. So, let us go to the map which is little larger. So, again this is the Ferryghat, same area, this area is Harindungri, and we see the 3 quartzite bands are synthetically deformed with respect to the regional deformation. So, to interpret this, we actually can take these 3 bands as a single layer. For the time being, we can avoid this minor faults here and there, and let us see what we can interpret out of this. So, we can consider, as we have said, that let us put this as a single band, something like that, and consider this as a horizon, because we are trying to interpret the overall deformation. We will try to simplify the entire thing in terms of regional features, and this is where we have Ferryghats and so other things. Now, what we have seen in this entire place, that if we try to now plot or consider the data in and around, then we see that here the fold axis F1, let us mark it this way, this is F1. Okay. F1 here is like this, and 20 degree is the plunge. If we come here at this place, the F1 we encountered, they more or less have the same orientation, but the plunge is 70 degrees. Okay. If we talk about the overall dip and strike of this 3 quartzite bands, then once we come here in this side, the strike is like this, and dip here in this region it varied little bit. So, it was around 50 degrees to 70 degrees. If we come here, dip is more or less consistent here and average value is around 60 degrees, and in this side if we come here the dip is around 45 degrees. Now, what is important here that we see that if I consider this is fold, then the dip of the bedding plane or dip of the S0 is towards the core of the fold, and that tells you that this is our first interpretation, that this is scene form. From the shape we can also see that it has two hinges, one here and another here. That also tells you the geometry of the fold. We can say that this is a box fold. Okay. We have seen number of sedimentary features that gave us the Younging direction. For example, in the first quartzite band we have seen a number of cross beddings and overturred cross beddings that gave us the idea that Younging direction is towards the core of this scene form. So, the third information that we get from this fold is that it is syncline. So, the fold is synformal syncline. Now, let us talk about the plunge. Okay. Fold is of course plunging fold. Here it is much higher, here it is much lower, but this is a plunging fold. Because the plunging of the fold is not consistent throughout the area, so we can clearly say that this is a non-cylindrical fold. And from many small scale features we have identified this. Okay. So, what we see here that we can actually interpret all these things, and we can also see that dip in this side of this limb is much less compared to the dip that we have encountered in this side, in this limb. We can define that this is northern limb and this is southern limb, and because their dip angles are different, we can also say that the fold is asymmetrical. So, you see a lot of information we can gather out of it, and these are essentially some 2 to 3 dimensional data that you can conceive. Here in Ferrighat this is a hinge zone, and here it is also hinge zone, and here this is also a hinge zone, and we can draw, we can consider that this is the axis of the scene form. It probably went to this side, this way. Okay. Here the plunge is much higher, and slowly the plunge of the fold axis is reducing towards the Ferrighat. So, the shape of the fold you can think in 3 dimension like spoon or a canopy, where it is actually like that. Okay. So, you have, this is where you are in the Ferrighat and it is going like this. So, you can interpret the fold. I am just trying to draw it like this. It just like a spoon. Okay. So, here you have this first hinge, for example, this one, here you have the second hinge, this one, and here you may have the Ferrighat, and this is how you are interpreting this. It can be interpreted in many different ways, given we have some other regional features, particularly it is near the shear zone. We have a big scene form just above this location with the Dalma volcanics and so on. So, eventually the interpretation of this region, if you go through literature, is extremely complex, including the faults and so other things. But for an undergraduate course, in my opinion, this is the simplest way we can learn this. and you are more than welcome to interpret things and read more, expand your area by adding data from the literature and other features. You always have the maps of Professor Naha that I have shown, and also Sarkar and Saha. From there you can gather and try to understand the regional deformation of this region. That was in particular not the key purpose of this course, but to give you an idea how to work in the field, and therefore I did not go to the complex interpretation of this area. So, with this I conclude this field course. I hope you have enjoyed these lectures and learned something, particularly those who could not go to the field because of pandemic. From my side, I have to acknowledge a number of people, and you can see their names after each and every lecture, but I particularly like to mention the Media Center and NPTEL staff from IIT Kanpur, the editors, those who recorded these lectures in studio and also in the field. And I must thank the TAs who were involved in this course since the beginning, and they are Rajiv, Tushar and Pushpendu. They worked enormously in making this course successful, and all our efforts actually would be effective when we feel that you learned something out of it, and this is why we all worked hard for your general understanding of field structural geology.